Welcome to session 14 of Dr. Donald J. Wheeler's Understanding SPC seminar. This session begins with a standard measure of relative utility known as the intra-class correlation. The intra-class correlation characterizes how well a particular measurement system will work with a specific production process. With the intra-class correlation, we can define 4 classes of process monitors that allow us to understand when and how to use less than perfect data in practice. Short EMP studies will allow us to find both the probable error and the intra-class correlation without the complication of nuisance components of measurement error. Finally, we will look at basic EMP studies where we explicitly consider nuisance components of measurement error. This session will use evaluating the measurement process, where we begin on page 47.
The traditional measure of relative utility was introduced by Sir Ronald Fisher in 1921 and is known as the intra-class correlation coefficient in our context. In terms of our model, where the variance of the product measurements is the sum of the variance of the product stream and the variance of the measurement errors, the intra-class correlation coefficient, denoted generally by rho, is the variance of the product stream divided by the variance of the product measurements x. This simple ratio correctly and properly defines that proportion of the total variation, variance of x, that can be attributed to the product stream, the variance of p. Likewise, the complement of the interclass correlation, 1 minus rho, will be the variance of the measurement system, E, divided by the variance of the product measurements, X, will define that proportion of the total variation that can be attributed to measurement error. The usual estimate for the interclass correlation coefficient is the interclass correlation statistic, 1 minus the estimated variance of E divided by the estimated variance for X. When measurements are based upon multiple determinations, it will be fairly easy to obtain these two estimates. To illustrate this, we'll use the viscosity measurements for product 10F. A sample from each lot is split, and the viscosity is determined for each half sample. The average of these duplicate readings is the value that gets reported for each lot. The ranges of these duplicate readings will characterize the measurement error, and the lot-to-lot variation will be captured by the moving ranges computed from the averages. So here we have a three-way chart. Using the average range of 61.4 centistokes, we estimate the measurement error for the average of two readings, sigma E hat, to be 38.5 centistokes. Using the average moving range of 917.5 centistokes, we estimate the total variation of the reported averages, sigma hat x, MR bar over D2, 813 centistokes. Once we have these two estimates, we can compute the interclass correlation statistic, 1 minus 38.5 squared over 813.4 squared is 0.998. 99.8% of the variation in these averages comes from the product stream, while 2 parts per thousand come from the measurement system. So for product 10F, there is no real need to use duplicate testing. Single determinations will suffice. When single determinations are used, we may have to obtain our estimates for the variance of E and the variance of X from different charts. Returning to the example we saw earlier in the workbook, product 2131 measured using test method 56 and a consistency chart for test method 56 provides an estimate of our measurement error and our probable error. The weekly measurements of a known standard value, accepted value being 40, by test method 56, the average moving range is 2.13. So sigma E hat will be the 2.133 divided by D2, 1.128, gives about 1.9. So our probable error is about 1.3. These measurements are good, plus or minus 1.3 units. Half the time the error by more than that, half the time the error by less than that. An average and range chart for product 2131 may be used to obtain an estimate of the total variation. So here we have subgroup size 8, a subgroup from each day's production, and our average range is 7.8 with a subgroup size of 8. Sigma X hat is R bar over D2, 7.835 over 2.847, 2.752. So sigma X hat squared is 7.574. When we combine these two estimates, we can compute the interclass correlation statistic that characterizes the relative utility of using test method 56 for measuring product 2131. 1 minus sigma E hat squared over sigma X hat squared gives us a 0.528. When this process is operated predictably, only 53% of the routine variation in the measurements will come from the product stream for product 2131. And 47% of the variation in the measurements will come from test method 56. Now, while an interclass correlation of 53% may not inspire confidence in the measurement system, this measurement system is still sufficient to detect the fact that this production process is being operated unpredictably. So we see that process behavior charts can work with less than perfect data. The effect of measurement error is to inflate the limits. This means that any signals you find on a chart are very likely to be real signals which deserve to be investigated. When confronted with a chart like the one for product 2131, the question is not, how good are the measurements, but rather, what are the assignable causes of this exceptional variation? When the chart shows signals of exceptional variation, it is a mistake to spend your time and effort on anything other than looking for the assignable causes. So even though the intra-class correlation is only 53%, the measurement system is good enough to detect the problems with this process. Until you fix the production process, it is a waste of time and effort to worry about the measurement system.
We now use the intra-class correlation to define different classes of process monitors. These classes are summarized in Chapter 4, but are explained in detail in Chapter 15 of Evaluating the Measurement Process.
Well, if we can use a measurement system that has a relative utility of 53%, how small does the interclass correlation have to be before the measurements become useless? To answer this question, we will consider three aspects of how measurement error affects our ability to use measurements. Number one, how a production process signal gets attenuated. Number two, what is the likelihood of detecting a process shift? And number three, what is the ability to track process improvements? Now, the answer to these questions is covered in Chapter 15, but we're going to just go over the highlights instead of getting lost in all the mathematics behind it. But we will pull some information out of Chapter 15. So, from page 202, measurement error will tend to attenuate signals coming from the production process, according to the curve shown here. The relationship between process signal strength and intra-class correlation is nonlinear. The production process signals will have a strength equal to the square root of the interclass correlation coefficient. Measurement error affects the likelihood of detecting a 3 standard error shift. And how it affects it is shown on page 205. Now, this graph is the graph that is on the cover of the book. The amazing thing is that these curves stay as high as they do, as long as they do. One curve is for detection rule 1 alone, a point outside 3 sigma limits. The other curve is for all 4 rules in the Western Electric zone tests. The way that the capability ratio changes with the interclass correlation coefficient is shown on page 208. The capability ratio will increase as the intra-class correlation decreases. So C sub P is a function of the square root of 1 minus rho. That's the curve shown here. So these are the mathematical relationships behind the impact measurement error has upon our ability to use the measurements. Now, what does that mean? Well, back on page 52. A first-class monitor will have an intra-class correlation greater than 80%. If you have a first-class monitor, any signal coming from the production process will be attenuated less than 10% when those signals show up in the product measurements. With a first-class monitor, detection rule 1 alone will give you better than a 99% chance of detecting a 3 standard error shift. And we can track process improvements with a first-class monitor up to the point where the capability ratio reaches the crossover capability CP80, which is given by this formula here. Any improvement in process, any reduction in the process variation will simultaneously decrease the interclass correlation while increasing the capability ratio beyond this point. Second-class monitors are those with a interclass correlation between 80% and 50%. With a second-class monitor, any signal coming from the production process will be attenuated anywhere between 10 to 30% when those signals show up in the product measurements. With detection rule 1 alone, we will have better than an 88% chance of detecting a 3 standard error shift. With all 4 detection rules, our chance of detecting a 3 standard error shift climbs up to 100%. And we can track process improvements with a second-class monitor up to the point where the capability ratio reaches the CP50 crossover point defined by this formula. If you get to this point, any further improvement or reduction in the process variation will increase your capability bigger than this value, but it will reduce the interclass correlation to less than 50%. If you have an interclass correlation between 50% and 20%, you have a third-class monitor. Here, any signals coming from the production process will be attenuated by 30 to 55% when they show up in the product measurements. Using all 4 detection rules, we will have better than a 91% chance of detecting a 3 standard error shift with our third-class monitor. We can track process improvements up to the point where the capability ratio reaches the value CP20. And CP20, the crossover capability, that interclass value of 20%, is effectively the upper bound on the capability that you can detect using this measurement system with this production process. Interclass correlations below 20% represent fourth-class monitors. With a fourth-class monitor, any signal coming from the production process will be attenuated by more than 55% when it shows up in the product measurements. The chance of detecting a 3 standard error shift rapidly evaporates in this zone. Moreover, we cannot track process improvements with a fourth-class monitor. With a fourth-class monitor, it's very hard to detect process changes and virtually impossible to detect process improvements. For that reason, any use of a fourth-class monitor is an act of desperation. So, A measurement system has utility whenever it is a first, second, or third class monitor. First, second, and third class monitors may be used to detect detrimental process changes and quantify process improvements. This means you can successfully use first, second, and third class monitors with the problems of representation and prediction. We may have skipped over that in this class, but that's defined back in chapter 1. So while the probable error solves the description problem and the characterization problem by giving us an absolute characterization of how good the measurements are, the interclass correlation gives us a relative measure of utility. It tells us when a measurement system can be used with representation and prediction.
While we were able to use existing charts in the previous examples, there are times when we will need to conduct a special study to compute both the probable error and the intraclass correlation. The simplest of these studies will be a short EMP study.
So on page 54, having defined ways to characterize the quality of a measurement in both an absolute sense and a relative sense, and having shown these summaries to be both theoretically sound and easy to interpret in common sense and practical terms, we now turn to the problem of evaluating the measurement process. In an EMP study, we will need to differentiate between sources of measurement error. Up to this point, it's just been measurement error, generic and undifferentiated. Now we're going to start talking about the components of measurement error. Test, retest error will be the core component. Sigma PE hat squared, pure error. This is known as repeatability or equipment variation and other terms. I just call it test, retest error because I think that's descriptive. But the traditional label here is pure error. It's the basic core component. Now, operator contributions to measurement error are a nuisance component when they are present. So you might have a component of measurement error, sigma squared sub O, that represents the effect of the different operators. Instrument-to-instrument differences are another nuisance component. Call it sigma squared sub D for devices. And if you had both operator and device differences present, your measurement error might consist of pure error plus operator plus device components. So that's the notation we'll be using in what follows. On page 55, a short EMP study. With product 2131 and test method 56, we needed both a consistency chart and a process behavior chart to obtain our estimate of the interclass correlation. And frankly, that's the preferred methodology, if you can. But when either one of these two charts is not available, we may have to resort to estimating the interclass correlation by using a short EMP study. In a short EMP study, K samples of a single product are measured N times each by one operator using one instrument. These NK values are displayed on an average and range chart as K subgroups of size N. So, on page 55, 56, how does gauge 702 work with process 833? 10 samples of product 833 are selected and labeled. Each was measured using gauge 702. Then each was measured again using gauge 702. Finally, each was measured a third time using gauge 702. And we like to do it this way so that it's more complex than simply measuring one part 3 times in a row. It gives us what we feel like is a more realistic test-retest value. So in this case, n equal to 3 and k equal to 10. There's nothing magic about subgroup size 3. Quite often you'll see we're using a subgroup size 2. It's a choice. So here we have our average and range chart for this short EMP study. Here, the retest error is isolated within the subgroups. The product variation shows up between the subgroups. So the range chart will characterize our retest error for gauge 702. Here, the range chart shows no evidence of inconsistency in the measurements from gauge 702. So sigma PE hat would be R bar divided by D2 times the square root of the number of replicated readings used to report a value in practice. So here our R bar is 0.92. D2 is 1.693 because our subgroup size is 3. And the number of replicated readings used in practice is 1. So sigma PE hat's 0.5434. That means our probable error, 0.675 times sigma PE hat, is 0.37. So the smallest effective measurement increment is the probable error divided by 5. That's 0.07 units. So here, the data are recorded to 1/100th of a unit, but they're only good to plus or minus 7/100ths. So while gauge 702 gives you 2 decimal places, the values are only good to 1 decimal place. They need to record 1 less digit with gauge 702. Now, the average chart shows the relative utility of gauge 702 for measuring product 833. And to see this, we have to compare 2 bands. The running record shows the product variation, the green band here. But the limits, the pink band, are based solely upon test-retest error. So the narrower the limits are relative to the running record, the larger the intra-class correlation is going to be. To estimate the intra-class correlation, we need to estimate the product variation and combine it with an estimate of test-retest error variation already obtained from the range chart. We capture the product variation here using the range of the subgroup averages. The range of the product averages, R sub P, 3.386. Sigma p hat is the range of the p-values divided by d2. So that's 3.386 over the d2 for 10 values. We use that value for d2 because the range here was the range of 10 averages. We get a 1.1. So the sigma p hat squared is 1.1 squared, 1.121. Sorry, 1.21. Since variance of x is equal to variance of p plus variance of e, we can write the intraclass correlation as sigma p hat squared over sigma x hat squared equals sigma p hat squared over sigma p hat squared plus sigma pure error hat squared. So sigma p equal 1.1 and sigma p equal 0.5434. We square each of these. We form the ratio and sum. From these two values, we estimate the interclass correlation for using gauge 702 to measure product 833 as about 80%. 80% of the variation in these measurements actually comes from the product stream, while 20% of the variation in these measurements comes from the measurement system. So gauge 702 provides a first-class monitor for use with product 833. Our next example will involve several short EMP studies. It's a round-robin study that was used to evaluate the abilities of 6 laboratories in measuring the silica-producing volatiles for each of 6 silicon sealing compounds. These compounds are the sealants used in place of gaskets in your automotive engines. They're all silicon, but they all have different curing systems. And the different curing systems give off different volatiles. And if the volatiles contain silica, then the silica will foul the engine oxygen sensor and the car won't run. So it's important to know about the silica-producing volatiles for the sealant you're putting in the engine. To test this, a slab of sealant is laid out on a piece of glass and cured for 24 hours under fixed conditions. Then 3 coupons are cut from the slab, dissolved, shot in a gas chromatograph. A siloxane calibration curve is established, and the silica-producing volatiles are read from the curve. And the average of these 3 readings is the reported value. So this is a complex laboratory test that takes over 24 hours to conduct. So you better get it right. Supplier A can detect the difference between the 6 different compounds in terms of the silica-producing volatiles they yield. Compound 2 is low, and compounds 5 and 6 are high. Sigma E for his average reading is a little under 3. So his probable error for the average reading is basically 2. Supplier lab A produces values that are good plus or minus 2. Supplier lab B is the reference lab. They developed the test procedure everyone else is using. Their sigma E for averages is 1.31. So their probable errors for averages is about 0.9. They produce numbers that are good plus or minus 1. And the difference in their grand average and the grand average for lab A is a potential bias between the two labs. But because these are the same 6 compounds, we expect to see, and we do see, good parallelism between labs A and B. Laboratory C has a probable error for averages of 4.87. So while measurement error makes it hard to detect the differences in the compounds, except for that first point, the average chart still shows a reasonable parallelism with labs A and B. The lab C reported values are good to plus or minus 5. Laboratory D, with a median range of 4, these limits suggest that supplier lab D has a potential to be a good lab. However, the 2 ranges above the limits on the range chart show a problem with the consistent application of the measurement procedure. Moreover, compounds 4 and 5 need to be higher up to get good parallelism. Probable error here is about 1 unit when they learn how to do the test. I think we're looking at learning effects here in this chart. Laboratory E, reasonable parallelism with lab B, a potential bias relative to lab B, probable error is about 1.1, so another good lab. And then we have the customer lab. The customer lab is consistently measuring something different than the other 5 laboratories. To get any sort of parallelism, you would need to turn their average chart upside down. The grand average shows serious bias. The probable error for averages of 2.2 doesn't mean much when you are consistently and repeatedly measuring the wrong property. Computing the numbers does not take the place of looking at the graph. The problems of lab C and D and the customer lab show up on the graphs. The biases between the labs show up on the graphs. The values we compute merely complement the graphs. Computing the intra-class correlation and the probable error cannot take the place of looking at the data. You learn more in 10 minutes with an average and range chart than with a handful of summary statistics in ANOVA tables. And that's not just my opinion, that's what my students keep telling me.
Different labs have different amounts of measurement error. These differences between the labs are an example of a nuisance component of measurement error. One way to isolate, detect, and estimate potential nuisance components of measurement error is to use a basic EMP study.
Nuisance components of measurement error are components that unnecessarily degrade the quality of the measurements. In the round-robin study, if the differences between labs remain unidentified, what kind of chaos would result? For example, which compounds would the customer lab pick as having low silica-producing volatiles? Let's go back and look. A, B, C, D, and E all show 4 and 5 or 5 as high. The customer lab would pick 4 and 5 as low. Nuisance components of measurement error can really mess things up. So we need to be able to identify them and get rid of them. Now, since Chapter 6 will require a shift in how we interpret our charts, it will be helpful to consider how different contexts result in different interpretations for the results of our analysis. No data have meaning apart from their context. Context tells us how to analyze our data and interpret the results of our analysis. Even when we use the same technique, we may end up looking for different things in our analysis, depending upon the context. Observational studies. We use the stream of process data with a chart to characterize process predictability. We either detect assignable causes of unpredictable processes, or we estimate the parameters of a predictable process. But with an observational study, signals on the process behavior chart represent problems for the process that need to be fixed. Consistency charts. Periodically, we measure a standard item or batch and place these repeated measurements on an XMR chart to characterize the consistency, that is, the predictability, of the measurement process. If consistent, we can estimate the probable error. If inconsistent, you have a rubber ruler. Signals on the XMR chart represent problems for the measurement process that need to be fixed. Experimental studies. Here we use a structured experiment to systematically vary inputs in order to detect, verify, and estimate suspected cause and effect relationships. The objective is to create signals. Signals on the average chart are expected and desired. Signals on the range chart are potential problems. And see, this is what we were doing with a short EMP study. Pollock variation caused us to expect points outside the limits on the average chart. But signals, points outside the limits on a range chart, would be a problem with the measurement system. Now, in chapter 6, we're going to be talking about evaluating the measurement process. Here, we're going to use a structured experiment with repeated measurements of selected parts or batches using different operators and/or different instruments to estimate the probable error of the measurements and detect any nuisance component that might be present. Detectable differences between parts or batches are good. Detectable differences between operators or instruments are problems that need to be fixed. Also, signals on the range chart are problems with the measurement system. So, same technique, but the way we interpret our results is changing. Here we're going to have good signals and bad signals to deal with. So, chapter 6, page 67. Some common nuisance components are biases between operators, biases between instruments, biases between labs, etc. Differences in test-retest error between operators, between instruments, or between labs, etc. A basic EMP study allows us to identify nuisance components of measurement error so that we may eliminate the corruption they create. So operator effects are perhaps the most often studied potential nuisance component. Here, a basic EMP study would typically consist O operators measuring each of P parts N times each. These NOP data are arranged into K subgroups of size N and placed on an average and range chart. Gauge 109 measured parts to the nearest micron. To evaluate this new gauge, Richard had 3 operators measure each of 5 parts twice. He then created the following average and range chart. With this organization, Richard placed the operator-to-operator differences and the part-to-part differences between the subgroups. And he isolated the test-retest error within the subgroups. You see, measurement error is always present. And the only way we can isolate it is to leave it within the subgroups and make everything else show up between the subgroups. And that's the operating principle behind EMP studies. So with this organization, what does the chart tell us? With this organization, the range chart will check for consistency of test-retest error. No points outside the limits, we have consistent test-retest error. The limits on the average chart are based on the average range. That means the limits on the average chart will show that amount of variation, which is obscured by measurement error. At the same time, the height of the running record on the average chart shows the product variation plus any biases between the operators. The height of this green band we want to be bigger than the limits on the average chart. So in an EMP study, we want no points outside the limits on the range chart. But product variation alone should produce points outside the limits of the average chart. So the first question we ask of a basic EMP study is, does the average chart show a reasonable amount of parallelism between the operators? I mean, they're measuring the same 5 parts. We'd like them to agree on which parts are high and which parts are low. Gauge 109 shows good parallelism, with all 3 operators agreeing on the relative sizes of the 5 parts. Any substantial lack of parallelism will indicate the presence of a serious interaction effect between the operators and the parts. You do not want the operators to interact with the parts when measuring them. We do not want the operators to measure the parts differently. So any such interaction effect is a serious type of measurement inconsistency, which will need to be investigated. The second question we ask of an EMP study, do the operators display a similar amount of test-retest error? All those ranges look more or less the same. If they do not, one operator will have larger ranges than the others, and you may need to analyze your data using an analysis of mean ranges, an ANOM-R chart. We'll talk about that shortly. The third question we ask of an EMP study, do the operator averages appear to be reasonably similar? If you suspect there is a detectable bias between the operators, you can analyze the data using an analysis of main effects, ANOM-E chart. You'll hear about that in a moment. For gauge 109, we have good parallelism, similar test-retest error, similar operator averages. So we proceed to characterize this gauge for measuring these parts. From the range chart, we can obtain the probable error. Sigma PE hat equals D2 times the square root of n sub r. So here our subgroup size is 2. Our R bar is 8.933. Our D2 would be 1.128, and our n sub r, we do 1 reading in practice, so n sub r is 1. Sigma PE hat is about 8 microns, so our probable error is about 5 microns. While these measurements are recorded to the nearest micron, they're good to plus or minus 5. To estimate the relative utility of gauge 109 using the intraclass correlation, we need to estimate the product variance via variance of P. In an EMP study, we can obtain this estimate from the parts used in the study. We begin by finding the grand average for each part. The range of these 5 averages is 41. And sigma p hat squared would be the range of the part-to-part averages squared over d2 squared. So that's 41 squared over d2 squared. And the d2 we use here is the d2 for 5 items because the range spanned 5 items. And we get a sigma p hat of 310.7. So sigma p hat squared, pe hat squared, 62.7. Sigma p hat squared, 310.7. And our intraclass correlation is 0.832. %83% of the variation in these measurements actually comes from the product stream. 17% of the variation in these measurements comes from the measurement system. When used to measure these parts, gauge 109 is a first-class monitor. And first-class monitors are those where measurement error has very little impact upon the measurement process. So we look at the graph and you can almost read it right off the graph. Good parallelism, similar test-retest error, similar operator averages. We can compute the probable error at 5 microns. Interclass correlation is computed to be about 83%. And if you want a flow chart for the steps in this EMP study, you can find those on page 70 in EMP3.